I think is what I can do. All right, perfect. All right, so welcome everybody to the August meeting of the Central Virginia chapter of the American Meteorological Society. I think we have a really great and awesome meeting for you guys here today. With us, we have Richard Griffith, all the way from the UK, who's going to talk to us a little bit. And then our speaker tonight is Dr. Love from the USGS, talking about the Geomagnetic Observatory at Fredericksburg. So thank you all for being here. First on the agenda tonight, we'll kick off kind of the meeting here, is chapter elections. So congratulations to myself and Dan and Tom for getting another year of service. I mean, volunteer. No, as your executive committee. Yeah, I really appreciate everybody doing the online elections this year. I know it's been a little tough being virtual, so I'm really happy that everybody was kind of flexible, and we're a little late and not exactly the method that we're supposed to. So I appreciate everybody that participated in that. But speaking of virtual events, we have Chris White here with us tonight. He's the organizer and organizer of the Mid-Atlantic ChaserCon. For everybody that doesn't know, the Mid-Atlantic ChaserCon is an annual event. We've had it for the last 2 years here in Richmond, Virginia, trying to build a community for the storm chasing community, the Mid-Atlantic region. Chris, do you mind giving a quick little update on what's happening this year?
Sure. Well, as we all know, we've been forced to Zoom calls and virtual meetings, and so we did the same thing. I don't feel like we're in too bad a company, though, since the National Weather Association and the American Meteorological Society have both taken their annual meetings virtual this year. So what we have done, or what we are actually in the process of doing, is setting up our virtual meeting, and it's actually going to be meetings, plural. What we've decided is, because of everybody doing this all the time, there's a lot of Zoom fatigue around, if you will. So what we're going to do is spread it out over 4 separate Saturdays for 1 hour each Saturday, starting the October 24th, and then the 31st, which of course is Halloween, and then November 7th and November 14th. And what we're going to do is have one speaker on each day. It will be from 11 a.m. to 12 noon Eastern time. First 2 sessions, that would be 15Z. And then the second 2 sessions, that would be 16Z, because of course we have a time change in there. So we're in the process of setting that up. It's going to be hosted by and broadcast, live streamed and hopefully broadcast by local television stations in Virginia. So the first one on October 24th will be hosted and live streamed by WDBJ7 here in Roanoke. The chief meteorologist, Brent Watts, will, I guess, be co-hosting with me. We're still working those details out. And our speaker will be, excuse me, just need to mute when I do that. But our speaker will be Jeff Halverson, Dr. Jeff Halverson of the University of Maryland, Baltimore campus. He'll be talking about derechos, which should be on everybody's mind, especially given the one that just smashed Iowa here recently. But I think he's specifically going to talk about the derecho that went through Pennsylvania and New Jersey and hit Philadelphia back in June, I believe it was. But he's out there. He's done a lot of research on derechos. I think he's actually coming out with a severe weather textbook this week or this fall as well. So we'll be having him talk. We're still working on speakers for the other types, other dates. The final date, which is November 14th, we're going to have a panel of storm chasers talk about, pick their favorite chase here in the Mid-Atlantic this year. And so far we have 2 people set up to do that. We're looking for a 3rd speaker. I've got feelers out. So that'll be wrapping things up. But that's our Mid-Atlantic ChaserCon, which we normally have on one day on a Saturday, spread out over 4 days, and it'll be virtual. And we're not anticipating any charges, so it'll be free to anybody who wants to tune in. And we'll get all the live stream details and everything out for that.
Wonderful, thank you, Chris. I think it's going to be a fantastic meeting again this year. For everybody, the past 2 years have just been wonderful. So I really encourage everyone to tune in this year.
Chris, quick question. Was Audrey going to contact Jim Duncan?
Actually, Brent Watts is.
Oh, okay.
Yeah,
Cool.
Brent is going to be talking to Jim Duncan and Aubrey, also her station. We're looking at those 3 stations doing the hosting. I haven't heard any details about that yet, but yeah.
Okay. Thanks.
And also, let me throw this out there for the chapter. I really appreciate the chapter's support the last couple of years for handling the registration table and just being part of the planning staff. It's been a big help. I appreciate you guys.
Of course, our pleasure.
And hopefully maybe we can attract a few people from Richard's group in England to participate, perhaps. So you never know.
Yeah, that would be really good. We have you probably heard the organisation of Toro in here in the UK, and I've passed Dan's details to them already, so hopefully someone will be in contact with you. But if you send me the details across, that would be fantastic. I'm sure we get some members over here joining, especially with the time difference as well.
Right.
Chris, I can send you Richard's contact info.
Sure, and I'll put out the anybody that wants to know, you can go to the Facebook page, Mid-Atlantic ChaserCon. I usually have links there, or midatlanticchasercon.com has links on there too.
All right, excellent. That's a great segue. Next, I wanted to introduce our next speaker, I guess, Richard Griffith, who is from Sussex, England. He's a member of the Climatological Observation League. Did I get that correct?
Nearly. It's the Climatological Observers Link. Colin.
Link. Okay, Link. Yes. Okay. Yeah. Do you want to tell us about your organization?
Yes, certainly. If I can share a presentation with you, just a very short one. Let me bring up this one here. Okay, can everyone see that okay?
Yeah.
Okay, fantastic. Well, good evening, and thank you very much for inviting me to join this evening. I know Dan joined us for our COL meeting, the Zoom meeting last week, which was very nice to have along. So the COL is the Climatological Observers Link, and it's the largest network of mostly amateur observers in Europe. And this year we actually celebrate the 50th anniversary of the organisation. We have about 350 members, mainly in the UK, but we do have some abroad, including some from the US as well. COL publishes a monthly bulletin which now runs to around about 50 pages, and this comprises of sort of anomaly maps of the month's temperatures, rainfall and sunshine. There's a daily synoptic development pages, day-to-day weather diary, and any interesting weather of noteworthy weather, and letters pages, and there's a worldwide weather roundup as well, and tables of members' data. You can see a typical sort of station we have here on the top one here, Carlton and Cleveland. This is in the north of the UK, so you have the thermometer screen and rain gauges. A lot of the members do use the Davis weather systems or automatic stations, which I guess you're obviously familiar with. They're very popular over here as well. But the organisation really goes back to the 1960s, when it first started, and this was the first advert which went out in the Royal Met Society journal Weather, and it was a gentleman up in Lancashire, and he put out a sort of a note of interest to other amateurs to see if anyone wanted to sort of get together and compare readings and things. Not a great deal happened until around about 1970, and this is actually the first, or copy of the first edition in May 1970. So on the left-hand side of the screen, there's a brief overview of the temperature and rainfall and sunshine for that month, and a few of the stations. Of course, it was all we were recording in Fahrenheit then, and inches, and there were a few stations. So if we fast forward now to 2020, the bulletin now is obviously all typed, and on the left-hand side you can see an example there of the daily weather summary, which is compiled and gives the extremes for all the various stations. on the day. And the right-hand page just shows one to do with the noctilucent clouds, which were around earlier in the year, and with some other cloud photographs. And again, there's members send in reports of any interesting weather there. A lot of the data is now tabulated, and this is an example of the page with the number of the stations, with the temperature, rainfall, sunshine, and the days of sort of frost and fog and things like that. So that's quite extensive across the UK and certainly further afield. We do have a fairly close link with the Royal Meteorological Society here in the United Kingdom. And the Royal Met Society hold 3 conferences a year. They hold the Professionals Conference, they hold a Student and Early Career Science Conference, which is always very well attended and very popular for those just starting out in their careers. And then we have an amateur conference, which again is very well attended. But of course, this year, unfortunately, we weren't able to hold it like a lot of people because of the COVID situation. And so I've hosted 2 Zoom meetings so far this year with members joining from across the UK, and I'm delighted to say that we had Dan and we had Rudy Nickman from Newark, New Jersey, join us as well, which was good. And I'm certainly hoping to plan future meetings for the members as we progress in the year. So just to round up a little bit about myself. I'm located in Sussex, around about 30 miles south of London, where the little red dot is there, and about 15 miles from the coast. This is my station. So I have an automatic weather station in the screen with the various sensors and data loggers. There's a couple of tipping bucket rain gauges. This is the standard UK Met Office type of gauge we now use. As well as the standard 5-inch manual rain gauge. And I'm sure you'll probably be familiar with this one, which is the COCORAS gauge, which seems to agree extremely well with our standard 5-inch rain gauge. And I also record grass minimum and concrete minimum and soil temperatures as well. And this is our temperature graph. I know Dan will be aware of this. Last week we had somewhat a bit of a heat wave over here, certainly for our climate anyway. We had a number of days when the temperature exceeded 34 degrees or 93 Fahrenheit. And certainly some of the nights were particularly uncomfortable as well. They didn't get down to into the low 60s. But as you can see now, we've certainly dropped off a little bit, and it's certainly more comfortable. And we actually had the first significant rain since the 27th of April over here, and obviously the chat earlier. So if you've got any rain you want to send us, we'd love to have it. We're a little bit dry at the moment over here. And this was a plot I did of the 1-minute air temperatures when we were hitting the maximums. It started off on the 7th, which is the blue line. And for several days, we had temperatures in excess of 34 Celsius or 93 Fahrenheit. And it didn't really break until about the 13th when we dropped down below the heat wave threshold of 27 degrees. And just to finally finish up, we do love snow. I know you get a lot of snow over there on occasions. We don't tend to get that much. And certainly over the last few winters, we've had very little. But this was back in 2010. This was the maximum I've recorded. And this was 28 centimeters of snow. And the standard 5-inch gauge is sort of buried under here, which made some interesting readings. But yeah, we occasionally get some interesting weather anyway. So that's it from me. Thank you.
Well, thank you very much, Richard. That was really amazing. I love snow, so I'm really happy to see things like that. Yeah, and thank you very much for literally burning the midnight oil to come see us.
No, it's a pleasure.
Yeah, thank you very much. So with that then, Dan, do you want to say or give a quick update about the budget?
Yes, I will. We still have a budget. Let me get my notes. We, as of up to this moment, I should say. We have a balance of $193.42. Recent expenditures include a Zoom payment, which we are obviously using right now, and an State Corporation Commission license payment of $25. Yeah, Peter made that. So those are our expenditures of the last month or so. And that's where we stand. Anything else? I think that is all I have for the budget. But since I have the floor for a second, I wanted to shift gears for one other thing. And apropos to Richard's recent talk, his talk just now, I just saw this the other day on the 13th. The American Meteorological Society is starting something called AMS Weather Band. And you can Google it. It's amsweatherband.org. And it says, what is AMS Weather Band? From radar frequency bands to snow bands to precipitation bands, there's a number of bands related to weather. And now there's one more. The AMS Weather Band, a global community of enthusiasts committed to advancing our shared understanding and appreciation of weather. Join the band this fall. That's all I've got, but it certainly sounds of interest to a wide variety of people. And I notice it talks about, and even includes, it mentions global community, so I guess it's open for all. I can say you can, I signed up to get an email about it when it, I guess, becomes a little bit more formal. But amsweatherband.org, that's all.
Very cool. All right, thanks, Dan. All right, with that kind of concludes our business portion of the meeting. I'm going to hand it over to our speaker, Dr. Love, research geophysicist at the USGS. So, Dr. Love.
Thank you. You can hear me okay?
100%. Perfect. Thank you.
Just a quick question, though, for Richard. Richard, I appreciated your presentation. I'm just kind of curious, this kind of amateur, although I'm sure quality data, is it used by the Met Office in any kind of official way?
Yes, quite a few of us, including myself, I send in the monthly rainfall figures to the UK Met Office and Environment Agency here. And there is also another, well, not really an organization, but another group which is the, you may have heard it, it's called WOW, or WOW, it's Weather on the Web. And that has quite a few, well, certainly anything up to about 1 million observations. And some of that data is actually put into the numerical forecasting model at the Met Office. Because they've just got a sheer amount of data they can fill in sort of blanks around. So some of the data is definitely used, yes.
That's great. All right, thanks, Richard. So I'm going to share my screen. And maybe somebody can tell me if they can see my screen. Does that mean yes?
Not yet.
Not yet? Okay. Let me see, maybe I need to do something again. Share screen. Oh, I see, I have to press this button.
There it goes.
That should do it, yes. All right, folks, I want to thank Dan and Peter for inviting me to give this presentation. I was asked to talk about the Fredericksburg, Virginia Magnetic Observatory, and I have developed some content here for this specific talk. I haven't talked on this subject before. There's some other kind of general slides I have here, but I really do appreciate the interest in one of our oldest, kind of old school, but now modern magnetic observatories. So I'll just start off by saying I have a long title. At the USGS, I'm the advisor for geomagnetic research. I work in the geomagnetism program, which is a very small program in the USGS. It's part of the Geologic Hazards Science Center, and that in turn is part of the USGS, US Geological Survey's mission for natural hazards. I want to thank Kristen Lewis, who looks after the operation of these observatories and looks after the staff and the budget. And as I like to say, she has the hard job. I'm just a scientist. Also thank Paul Bedrosian, Anna Kelbert, Greg Lucas, Ben Murphy, and Josh Rigler, who are my scientific colleagues, and they are people who I depend on and learn a lot from, and I appreciate working with them. So on this slide, you'll see that, and if you can hold on one second, I'm going to close the door because my dog is barking.
Don't worry, I had to throw my cat outside the room already.
All right. So sorry about that little distraction. In this slide, there is a schematic depiction of the Earth and kind of its interior. And shown in these kind of blue arcs is a schematic representation of the Earth's magnetic field. So just briefly, the Earth's magnetic field is generated in the Earth's core, where there is essentially a process that amounts to a naturally occurring electric generator. It's electrically conducting. The fluid part of the core is flowing. That motion and the electrical conductivity sets up this electric generator. Since there are electric currents, there are therefore then generated magnetic fields. And those magnetic fields extend from the core of the Earth up to the surface, where we can measure them, for example, at the Frederiksborg Observatory. And they extend out into space, where the extent of the magnetic field is called the magnetosphere. That interacts with the sun and the solar wind, occasionally setting up something known as a magnetic storm, which is a temporary disturbance of the Earth's magnetic field. So during a magnetic storm, the magnetic field is time dependent, and turns out time dependent magnetic fields, by Faraday's law, can induce or generate electric fields in the Earth's interior. And since the Earth's interior, including the mantle, is that part of the Earth over the core, since that part of the Earth is electrically conducting, those electric fields can generate currents and in turn set up voltage differences across the extent of the Earth. That's a problem for the electric power grid industry, which is something project I work on. And I'm going to get back to that a little bit in a few minutes here. So anyway, that's a brief kind of whirlwind tour of geomagnetism from the Earth's core to space and back to the Earth's surface. Okay, I just want to briefly summarize our program. As I said, the USGS Geomagnetism Program is part of the Natural Hazards Mission of the USGS. We are also in turn part of the Department of Interior within the US government. So we're an agency within the Department of Interior, and the USGS represents the Department of Interior in high-level space weather coordination projects. The one that's most prominent is something called SWARM, which stands for Space Weather Operations, Research and Mitigation. Our responsibility is to monitor the Earth's magnetic field at a network of ground-based observatories. And recently we've also taken on a new, probably temporary responsibility for supporting a national survey of the continental United States, a magnetotelluric survey, which is a project interested in understanding the electromagnetic relationship, the relationship between magnetic fields and electric fields that are generated at the surface of the Earth. That kind of information can tell us about the interior structure of the Earth, and it's also useful for analyzing geoelectric hazards, which is something I'm going to talk about. So we report magnetic observatory data with high accuracy, resolution, and reliability. Those data are used by a wide variety of customers, including Air Force, NOAA, which has an agency known as the Space Weather Prediction Center, NASA, some foreign laboratories. They are used in industry, and they are used, of course, for academic research. We also are involved with the promotion of magnetic observatory operations around the world through an international consortium known as Intermagnet. And we have operational partnerships with the oil and gas industry that our data are useful for steering drill strings so that the oil and gas industry can access multiple reservoirs from a given drilling platform. We have a small but important and I think very productive research element within our program. And we are not blue sky research, but we still do interesting research, and it also is of societal importance. And that's the main thing I'm going to talk about today. 12 full-time employees, 14 observatories, by government standards, a small budget, $1.9 million per year for everything. Operation observatories, paying salaries, everything. And as I've already indicated, Chrissy Lewis is the person in charge of our operations. And if you want to contact her, that's her email address. All right, so let's get on with the discussion of Fredericksburg. This is a panoramic picture of the magnetic observatory part of the Fredericksburg Observatory. There are other facilities on this site, but this is the magnetic observatory part. It's the part that the USGS operates, and it is those are the buildings where we collect our data. Now, this is an oldish observatory. It was built in 1956, and in those days, the operation of magnetometers was quite labor intensive. There were multiple redundant systems. There were a need for recording things on photographic paper and so on and so forth, and a lot of issues with calibration, and that's why we have so many buildings. If we were to design a new observatory today, it would probably just have one or maybe two buildings, but these are the facilities we have. They used to operate analog magnetograms. Today they operate modern digital systems. And so over time, the operations at this observatory have changed and modernized. All right, I just want to briefly, and I'll whiz right through this, talk about the history of geomagnetic monitoring in the eastern United States in the vicinity of Fredericksburg. It was in the late 1890s that the U.S. Naval Observatory in Washington, D.C. first began monitoring in any kind of long-term dedicated way the Earth's magnetic field and its variations. Those operations continued from 1889 to 1894, but were terminated with the installation of electrified trams in Washington, D.C. In 1901, the Coast and Geodetic Survey established an observatory at Cheltenham, Maryland. This is the predecessor of the Fredericksburg Observatory. That observatory operated until the Fredericksburg Observatory began to operate. The observatory at Cheltenham had to be closed because it also there was also interference from the electrification of trams for its operations, so the observatory had to be moved. Now, I think it's kind of interesting and maybe even amusing, and I'll highlight it here with moving my cursor, that to establish the Fredericksburg Observatory, an act of Congress was passed. That doesn't happen so easily these days. It seems that Congress has a hard time passing very much. But in those days, there was dedicated interest in this issue, and they passed a bill to support the establishment of a new observatory, that one at Fredericksburg, and I'll abbreviate it FRD at various times. And it's actually just outside of Fredericksburg in a small hamlet and unincorporated part of Virginia known as Corbin. The Fredericksburg Observatory began operating in 1956, just in time for the International Geophysical Year, which commenced in 1957. The observatory at that point was really kind of a hive of activity. It was the headquarters for the geomagnetism program, and a lot was going on, especially during the IGY. There was coordination with foreign observatory programs. The geomagnetism program had responsibility for training a lot of foreign observers working at magnetic observatories around the world. The facility at Fredericksburg was used for all kinds of things, including gravity measurements, seismic measurements, meteorological and cosmic ray monitoring. In 1965, the services of the Coast and Geodetic Survey was dissolved in 1965, and its services, many of the services, were transferred to another agency, a short-lived one, known as the Environmental Science Service Administration. And in 1970, most of those services were transitioned to NOAA. But some of them were carved off and given over to the U.S. Geological Survey, including the Program for Geomagnetism and the Earthquake Program. So the U.S. Geological Survey, up to that point, had been kind of more geological oriented, acquired something that's really more geophysical, and expanded its set of operations. So you sometimes hear that NOAA is a descendant of the Coast and Geodetic Survey, and I just want to say that's only sort of true, because some of the Coast and Geodetic Survey responsibilities were actually transitioned to the USGS. All right, so up through this time, the data acquired at the magnetic observatories were essentially analog. They used a set of automatic photographic recording systems. The basic data product were hourly mean data. In 1982, digital operations commenced at Fredericksburg, and a new product, an important new product, was developed, which is 1-minute resolution data. So with digital automatic systems, you can collect a much greater quantity of data. And this really was revolutionary. This allowed us to analyze magnetic storms in great detail and coordinate the acquisition of data on the ground with space-based monitoring of the Earth's magnetic field. In 1991, the USGS and the Fredericksburg Observatory became part of the international consortium known as Intermagnet. So our operations are now coordinated with other geomagnetism programs around the world, including the operations at Fredericksburg. In the 2000s, the USGS began reporting data in near real time via the internet. And in 2012, we started reporting 1-second resolution data. So that's a brief survey of our operations. Now, I showed you just a few minutes ago a picture of the Fredericksburg Observatory. This is a picture of the Cheltenham Observatory that operated from 1901 to 1956. I think it's a great picture, and I'm always kind of happy to see this because they had a windmill on the observatory site. I don't know what Cheltenham looks like today. It's probably suburbanized, but it was fairly rural at that time. All right, so this is a plot that I put together for this presentation, and I want to talk about it for a few minutes. This is a history of geomagnetic observations in Maryland and Virginia, collected by the Cheltenham and Fredericksburg Observatory. So I'll just point out at the bottom here, the time scale. It's 1901, actually, is when the first data begin, up to 2019. And what's shown here at the top is the horizontal intensity of the Earth's magnetic field over this, what is it, 118-year period of time. Down here, I'm showing declination, that is the horizontal direction of the Earth's magnetic field. This would correspond to the direction that a compass points, all right? Compass doesn't point true north almost everywhere. There's a deviation of the compass needle from true north, and it turns out that changes. The horizontal direction of the Earth's magnetic field changes, and the horizontal intensity of the Earth's magnetic field changes. I haven't shown you the vertical component here because it's just too much to talk about. But the point is that over this 118-year period of time, there's a slow drift in both the intensity and the direction of the Earth's magnetic field. And that is a result of convection in the core. You remember in that first slide, I talked about a little bit about the convection in the core and how it sets up a natural electric generator essentially and generates the magnetic field, the main part of the Earth's magnetic field that we measure at the Earth's surface. That process in the Earth's core is complicated, and that's perhaps a hand-waving way to say that the magnetic field that it generates is not absolutely steady. It has some time dependence. And in fact, this time dependence is one of the reasons why magnetic charts are periodically updated, and that's one of the reasons why magnetic observatories were first established, was to monitor changes in the Earth's magnetic field, to subtract out disturbance periods so that we could better map this slow so-called secular change in the Earth's magnetic field. Now there's a few other signals that are interesting here. So here we have the Cheltenham time series, and here we have the Fredericksburg time series. And you'll notice that they're offset from each other. So we moved the observatory from Cheltenham, Maryland to Fredericksburg. And it's not just because they're at ever so slightly different latitude and longitude, but it's because they are sitting on different amounts of magnetized rock. All right, that magnetized rock amounts to kind of pretty much a constant field that is imparted to the measurements that we make at these observatories. And because the Cheltenham Observatory is on a little bit of a differently magnetized rock than the Fredericksburg Observatories, there's this little offset. Now, the thing I'd like to concentrate on, though, are these little kind of spiky features that you see in the data. All right, you see that they come and go, and it turns out that there is an 11-year modulation in those spiky features, and that's due to the sunspot cycle of the sun. When we have a lot of sunspots, we tend to have magnetic storms, and that causes these deviations in here in the horizontal component of the magnetic field. And you can even see it in the declination of the Earth's magnetic field. Just point out here, this is a magnetic storm right here. I'm highlighting it with my arrow that occurred in 1938. Quite interesting. Over the course of that storm, magnetic declination changed by several degrees. Hello, that means you could watch this magnetic storm on a compass. So that's a non-trivial variation in the Earth's magnetic field. And indeed, the fact that magnetic field variations are actually rather large in some respects is one of the reasons why rather simple magnetometer systems that have been in operation for 150 years, those analog systems before the digital era, is why we could record magnetic field variations and indeed record interesting magnetic field variations. Another thing up here, I'm highlighting a particular storm known as the Quebec storm. This is a storm which interfered a lot with the electric power grid system in Quebec, Canada, and caused a province-wide blackout. And I'm going to talk a little bit about that. So that's the hazard aspect of geomagnetism. And then finally, the other signal that is measured in these data, and if as a scientist, I love looking at data. There's actually a very faint kind of annual signal here. I'm pointing it out here down the lower right-hand part of this graph. And that is due to the modulation of the ionosphere over the course of a year. So we have seasons that affects the temperature, of course. We have cold in the winter and hot in the summer. The illumination of the sun on the Earth's ionosphere changes its conductivity and changes the shape and strength of a smallish dynamo that actually operates in the Earth's ionosphere. And that causes an annual variation in the Earth's magnetic field, which you can see in those data. There's also a daily variation, but that's much too high a frequency to see in this plot of data. So there we go. And let's see, okay. So I was alluding to magnetic storms. This is a motion picture, schematic, a cartoon maybe, that was generated by NASA, and it's useful for explaining things. So occasionally the sun gives off a burst of electrically conducting plasma. It's, if you like, a concentration of solar wind. That solar wind passes radially outward from the sun. And if it happens to be directed towards the Earth, it arrives at the Earth's magnetic field. So there we have the emission of the plasma from the sun traveling through space. It takes a couple days. And when it arrives at the Earth's magnetic field, it compresses the magnetic field on the day side, extends it on the night side. And occasionally there's abrupt reconnections of the magnetic field in the tail, which end up diverting charged particles into and out of the Earth's ionosphere, causing the aurora borealis. So that's a magnetic storm I'm describing. Aurora borealis are oftentimes associated with magnetic storms. And so it is a little bit ironic in some respects that a beautiful phenomenon, the aurora borealis, the northern lights, is associated with a magnetic hazard that is a problem for modern society and electric power grid systems. So there we are. All right, so I want to talk a little bit about that. And this is a schematic representation of space currents. So we have in this diagram, we have the Earth here represented on the bottom. This red vector here represents currents flowing in space. They could be in the Earth's ionosphere or in the Earth's magnetosphere. And again, since we have a current, we therefore have a magnetic field, and that's represented by these gray loops. And if this current is time dependent, then this magnetic field will be time dependent. And a time dependent magnetic field can induce, as I've already said, or generate electric fields in the electrically conducting crust of the Earth. Now, the crust of the Earth is complicated, and anybody at the USGS will tell you, will agree with that. Geology is an interesting science because the surface of the Earth is complicated. It's the Earth's surface that we have today is a product of eons of geological processes. And I don't think it's too surprising that the electrical conductivity structure of the Earth that we have is also complicated. It has different compositions in different places. So there's different mineralogy, there's different phases of rock, different water content, so on and so forth. And as a result, the electrical conductivity structure of the Earth is very heterogeneous. Well, in this heterogeneous Earth, we're having induced these electric fields. All right, so just schematically, we're depicting a region of low conductivity right here in the middle. And we have more conducting rock here on the right and also on the left. And schematically, we also have deployed, for discussion's sake, a power grid across the low conductivity part of the Earth. Well, this electric field would like to drive electric currents in the Earth, but it finds it difficult to do so in the low electrically conducting parts of the Earth. And if we happen to kind of short circuit that with a power grid, you would end up getting naturally generated electric currents flowing from one grounding point through the grid and out through another grounding point. And that is a problem for the operation of an electric power grid system. Operating an electric power grid system is all about control. You want to control the current that you have. And the grid is designed to support alternating current of a particular frequency. It's supposed to alternate about a zero baseline, and transformers in particular are designed for that. If now you come along and have introduced a quasi-direct current, it's a current which is changing rather slowly compared to the 50 or 60 hertz variation in the power grid. If you apply a quasi-direct current to that system, you can cause operational problems. In fact, you can damage electric transformers. And if you introduce a lot of current, to the power grid system, you could damage quite a few transformers. You can trip relays, capacitors, so on and so forth, cause operational problems which are not intended. Grid operators will see this, they'll try to compensate for it, and sometimes that helps, sometimes it just causes a cascade of problems in the operation of the power grid. So that, in kind of a nutshell, is what happened in Quebec and caused the blackout in the 1989 storm, that's sometimes known as the Quebec storm. All right, so this is a product of our program, which I would say I'm very proud of our team. We have been able to assemble a hazard map showing where in the continental United States we could expect to have rather high direct current voltages experienced on the national power grid, and also where we can expect to have rather low currents. So it's a hazard map. It shows us where the hazard, this geomagnetic storm hazard, is high and where it's low. And this in detail is the voltage that would be experienced on the national power grid system once per 100 years. So it's a rare magnetic superstorm that's coming along, inducing a lot of electric fields, driving a lot of currents through the power grid system, setting up those voltages. And this then gives us some understanding of where we have problems and where we don't have problems with this particular phenomenon. So I'll just point out a couple of things. One here is the scale on the right. It goes from about 1,000 volts down to something far less than 10 volts. 10 volts doesn't sound like much, and in fact, it's not very much. But 1,000 volts for a powered grid system, which is designed to have alternating current around a zero baseline, is actually the problem. 1,000 volts will drive quite a lot of current through the powered grid system, uncontrolled currents, and that's where you end up having problems with the transformer systems. It's interesting to see where the hazard is high and where it's low. There's very high hazard in the northern Midwest, especially between Minnesota and North Dakota. Also, interestingly, high hazard here in the eastern United States, where of course, pretty much half of the United States lives, and some very important cities, including Washington, DC, Baltimore, Philadelphia, New York, Boston. That whole corridor of cities along the eastern United States is also where we have rather high geoelectric hazards, as would be experienced during a magnetic storm. And it turns out, if you look at these voltages, one of the very highest is in Virginia. And isn't that interesting? And so this is a new product that we have. We're very proud of it, and it has gotten our tiny little program at the USGS some good press. This is a product that is of interest to SWARM, that interagency space weather program that I was talking about at the introduction. And it is also a demonstration of the role of the solid Earth in this space weather hazard. The reason the hazards are high in the northern Midwest and the reason they're high in the eastern United States is because the rock that's underneath those parts of the United States is a rather poor electrical conductor. And because it's poor, the currents, again, won't flow through it very easily and find kind of opportunistically a path to take through the power grid system, which is why the hazards for the grid system are high there. All right, so this is my last slide. This is a more detailed analysis of the 1989 storm for the vicinity around the Fredericksburg Observatory. All right, so what we have at the top here is a time series of magnetic field variation recorded at the Fredericksburg Observatory. It's recorded for this couple of days period of time for 1989, and we are marching through time. This vertical line here represents each moment in time, and that moment in time is in turn represented by these maps here at the bottom. What I'm showing here on the left map, is for Virginia, and Fredericksburg is located somewhere around in there. It's a map of the electric field over the course of time for this part of the United States. So we've taken magnetic field variations, we've taken those magnetotelluric survey measurements. I was talking about that before. Measurements that tell us the relationship between magnetic field variation and the electric field. It's a relationship that doesn't change in time. That relationship doesn't, even though the magnetic field and the electric field that get generated do change. So we have this relationship which is related to the Earth's conductivity. We marry that to the Earth's magnetic field and its variations, which we record at Fredericksburg. And from that, we can estimate the electric fields that are being generated in the solid Earth. And that's represented by these vectors here over the course of time. And you can see that these arrows have different lengths in different places, and they're bouncing around in time. The fact that they have different lengths in different places is the result of geologic heterogeneity, all right? Magnetic field over this kind of region is actually rather uniform, so it's well measured by the Fredericksburg Observatory, but the induction, the generation of electric fields is very heterogeneous due to that complicated structure of the Earth's conductivity. On the right here, showing the voltages that are actually realized in the power grid over time during the storm, again in the Fredericksburg, Virginia area, and showing how those voltages change for different power grid lines at different times. And over the course of this storm, the voltages are almost, on some lines, almost 1,000 volts. On other lines, they're very small. And this is useful information to the power grid industry in their projects for developing mitigation measures that might be taken in order to alleviate the hazards that are represented by these magnetic storms. So this is the March 1989 storm. It was a very intense storm. We know, however, that there have been historically even more intense storms. There was a more intense storm that occurred in September 1909, another one in May 1921. And some of you may have heard of something known as the Carrington event, which was a very intense magnetic storm that occurred in 1859. So it's a long time ago. Those are big honking storms, bigger than this one that occurred in 1989. But the power grid is of such importance to our society that we can't just afford to prepare the grid for magnetic storms that might occur every year or every 10 years or even every 50 years. It's so important that we need to develop a resilient grid system that could withstand a magnetic storm that could occur on the time scale of once per century or longer. And that's the reason why we're motivated to do this analysis. So there we go, folks. I very much appreciate the invitation to give this presentation, and I'm also happy to take questions. So thank you.
Awesome. Thank you very much. That was a wonderful presentation. I learned quite a bit. So we did have one question in the chat. I think we'll go to that one first from Jackie. Talking about in the news in the past couple of days, I guess there's been a dent or a dip in the magnetosphere over especially the Southern Atlantic and South America. Yes. Do you know anything about that?
Yeah. Yes, I do. Okay, I didn't know that was in the news, and because I just actually fielded a question from the public myself. That's one of my other jobs. I answer questions from John Q. Public, and so I guess this is in the news. Yeah. So the Earth's magnetic field, like I was saying, generated by the core of the Earth, the main part of the magnetic field, the part that kind of changes slowly, is not symmetric. That's why declination, for example, is what it is. That's why the compass doesn't point true north everywhere. There's a shape to the Earth's magnetic field. And it turns out, if you looked at the intensity of the Earth's magnetic field over the globe, you would see that in the South Atlantic, there's a noticeable low point, kind of a weaker part of the Earth's magnetic field over the South Atlantic. That, like declination, changes over time. The intensity or weakness of the Earth's magnetic field in the South Atlantic changes over time. That anomaly itself kind of slowly drifts and moves around. There you go. So this is interesting. It's interesting if you're using the magnetic field for navigation, and that's still done, especially, for example, by satellites. Satellites use the magnetic field sometimes for orientation. And it turns out that there's another kind of hazard related to the mid-Atlantic low. It invites charged particles coming from space to enter the Earth's, the near Earth part of space surrounding the Earth, and it can damage satellites. So satellites that drift over this mid-Atlantic low also sometimes experience data glitches, which are due to charged particles passing through their electronic systems, and so on and so forth. So that is an interesting feature in the Earth's magnetic field. In some respects, it's not too surprising that we have a low somewhere. We have to have it somewhere. But that's where it is, and it has actually some real effects. So,
very interesting. Okay, thank you. I think I'll open it up to the floor. If anybody has questions, go ahead and unmute yourself, and we'll just try it that way.
I'm trying to figure out how to put myself back onto the screen.
I think it's, yeah, back down.
Stop sharing, maybe?
Yeah, yep.
Okay, so, stop share, here we go. Okay, that's great. I can go back to that if we need to, and
okay.
Depending on the question.
Well, yeah, actually, maybe.
Should I open the chat? Maybe that's what I should do.
Yeah. We had one question. The last site looks like the voltage follows right down the interstates.
Yeah, that is interesting. So I don't know, what is that? Is that I-95
995,
I've
64.
heard it's called that.
81, 85, all of them.
185. Okay.
All
So I'm sorry, I'm interrupting somebody. Yes.
I'm sorry. It looks like Interstate 64, 95, 85, and I-81.
Oh, okay. Well, it's not actually related to those highways themselves, but you know, to connect those big cities, you need big highways, and we have that kind of arrangement of cities and that coastline that we do because of the geology. So I guess maybe in a sense they're all kind of ultimately related. It's true that along those highways there tend to be high hazard, and it turns out that the lines that tend to be crossing the Appalachians or the Piedmont part of the geologic formations there tend to have the highest voltages. The lines that are oriented along the Piedmont or along the axis of the Appalachians have lower hazard. None of the lines though have such a simple geometry, they kind of snake around. But in terms conceptually, that's what's going on there. So
I noticed
yeah.
I noticed in your map that most of the southern to southwest
Oh yeah. Okay.
did not show a lot of hazards.
Yeah, I'm very happy you mentioned that. What I'm gonna do is pull up the map again. If I can move this share screen, share. Great, thanks for reminding me of this issue. Can you all see that map there?
Yep.
Okay, so sorry, I'm having to move these little windows around so I can see it too. That's right. So it's basically 2/3 of the United States that we have surveyed with this magnetotelluric method that I was alluding to. I'm kind of circling it there. This part of the United States, we're in the process of surveying it. And I alluded to some money that we got from Congress recently to support the completion of the magnetotelluric survey across this part of the United States. I can tell you, putting together this map, which shows 2/3 of the United States and shows where the hazards are high, where they're low, was one of the reasons why we were motivated to complete the survey across the rest of the United States. It demonstrates the utility of the magnetotelluric data, which is survey data, and them used in combination with the magnetic observatory data. So our leadership within SWARM, for example, wanted to see the completion of that survey across the southern United States so that we could more fully evaluate geoelectric hazards across CONUS. Thank you for reminding me. The few little things I sometimes forget to mention, but that's an important one.
I had another question.
Mm-hmm.
This is not so much geomagnetic based, but when you're doing your surveys, do you get from, whether it's around the world or here in the United States, any EMF from human-related activities like EMF on large cities and large highways? Do you see that as an interference?
Yes. So there's several things that can happen. Just for example, in operating the Fredericksburg Observatory, if somebody were to come into the observatory and drive their car past our magnetometer, it would disturb it. Cars, have some magnetization. And so, we try to keep the operation of our observatories pristine in that sense, to not allow just kind of, anything to happen near the magnetometer hut. With respect to the magnetotelluric survey, where you're measuring simultaneously electric fields in the crust of the Earth, which, by the way, you're just putting down a voltmeter and measuring the voltage difference across a length of line deployed across the crust of the Earth. We measured that voltage, which we can translate into an electric field, and simultaneously the magnetic field to find this impedance. That's a set of numbers that relate the two quantities, the magnetic field and the electric field. Now, especially depending on what frequency you're operating at, but generally speaking, that kind of survey measurement, which you just make at a particular site for a few weeks because the relationship between E and B doesn't change. So once you've measured that relationship, you can pick that system up and move it to a new site. If you plant that system down in the middle of a city, for example, you would have a lot of contamination. You'd have kind of quasi-direct currents related to trains. There's other interference. There just might be stray currents that happen to be flowing along pipelines for whatever reason. Just generally there's anthropogenic contamination that is a problem with these surveys. And so when you want to do this magnetotelluric survey, a big part of the project is finding the good locations where you can deploy these sensors, where you can get permission to deploy them, and where it's cool to operate them undisturbed for a period of a few weeks. So you can't see it on this map, but it's especially difficult in the eastern United States, where there's a lot of urbanization. And in particular, there's kind of a little island around New York City where there aren't any measurements, just because there's just too much built up around there. But they've done a pretty good job of finding locations. Some of the data are kind of noisy here for some kinds of measurements or some kinds of analyses. Those data are kind of noisy. For the kind of analysis that we're talking about here, where we're looking at big magnetic storms, we can tolerate a certain amount of noise in the tensors and those impedance numbers that we get from the survey to do this kind of analysis. So another great question. Thank you for that.
I was wondering, you're talking about the increase in voltage with these storms. Is there also an increase in amperage?
Yeah, there is. So what we are measuring in this map, for example, is a geophysical signal. That's a natural signal. So the electric field is being generated in the Earth's crust. And if you project that electric field onto the power grid line and then integrate it along that line, you get a voltage. Okay, so it's still a geophysical signal. Current, however, is a engineering signal. To figure out what that current is, you need to understand how those lines are all connected together, what the resistivity is on all the lines, what the resistivity is on all of the grounding points. And so that would be a calculation that is in principle possible if you had all of this information about line resistances, grounding resistances, and if you were able to accommodate the dynamic changing interconnectivity of the grid. You could in principle calculate the current that is would be generated on the grid itself. That involves, like I say, a lot of information. Some of that is not information that the power grid industry is super interested in sharing. But it's kind of a frontier, taking these geophysical signals like we show in this map, translating that into the response, essentially, of the engineered power grid system is really where there's a lot of work to be done, a lot of opportunities, but it's going to require a lot of cooperation between kind of a constellation of different companies that support these grid systems and the geophysicists that want to talk about the geophysical signal. So, yes. By the way, I'm happy to take any questions about magnetic anything.
Yeah, maybe one more question if anybody has one. Otherwise, it is just a little after 8 here. I was thinking maybe we should let people drop off the call if they need.
Okay.
I know Richard probably needs to get to bed.
Yeah. Hey, folks, yes. Sorry to mean to interrupt anybody, but I just want to thank you again for inviting me. I'm really happy to meet people who are interested in science. Meteorology is a science, of course, magnetism, different kind of science. And I am, I'm always just, as a scientist, I got into it because I find it interesting, and I'm happy to meet other people interested in nature and, its expression in terms of rainfall or wind, or in terms of induced currents on the power grid system. So thank you very much.
Excellent. Well, thank you very much. I think we all appreciated it a lot. It was very informative, very interesting. Really appreciate your talk tonight.
Okay.
Yeah. Oh,
Yeah, before you cut off, I mean, you can, I do have a question, but
Okay.
every once in a while you hear something rather extreme about the Earth's magnetic field might flip,
Yes.
which is hard to imagine. But what do you have to say about that?
Okay, that's great. I'm glad you asked that. That's what we would call a frequently asked good question. It's true. The Earth's magnetic field sometimes flips its polarity. This is not something that has happened over historical times, but it has happened over geological times, so very long time scales. And again, it's related to the dynamo, that process in the Earth's core that's generating electric currents and magnetic fields. And it turns out that the physics at play in the Earth's core is just as happy generating a magnetic field of one polarity as it is with the opposite polarity. And because the magnetic field is time dependent, what you end up getting is kind of a wandering of the Earth's magnetic field, where it kind of orbits or wanders around one polarity, but sometimes gets a little bit cattywampus. I like to use that word. And ends up drifting over to the opposite polarity. And then it just kind of orbits around that position for a while, and then kind of drifts over to the first polarity again. So that's the occasional reversal of the Earth's magnetic field. It does not happen periodically, okay? Just want to emphasize that. The core is too complicated, and so what happens is it kind of reverses essentially randomly. If you were to put together a time series showing the polarities of one or the opposite polarity, do a statistical test on it, you would have a hard time showing that it's not random. And that's interesting. So the Earth's magnetic field has this complexity and occasionally reverses its polarity. Now, put that in contrast with the sun. The sun's dynamo operates in a different parameter regime, and its dynamo reverses almost periodically. And that's what's related to the sun's 11-year sunspot cycle. All right. So the sunspot cycle is a waxing and waning of the number of sunspots, and that's related to the near periodic flipping of the sun's magnetic field. And then finally, I'll just say that's kind of two kind of possible time dependencies you could have, periodic, random, and the thing that we don't have on display here is steady. You could imagine there's a planet out there or a star out there that happens to have a slightly different parameter regime for its dynamo, and it just generates a magnetic field that basically just stays there, doesn't do very much. So these are just kind of different behaviors that dynamical systems can have. They can be steady, periodic, or kind of chaotic, and that's kind of a short physics explanation as to why it happens. Now, the last time we had a reversal, 780,000 years ago, that was a long time ago. Just put that in perspective. Homo sapien did not exist, all right? So that was a long time ago. It's way longer than anything that's gone on in history. 780,000 years ago. And it turns out that reversals happen randomly, but kind of on average once every million years. They take about 10,000 years to actually happen, all right? Who knows? Maybe our Earth's magnetic field is going to have another reversal, but we are not going to be around to know whether or not that's true, all right? So we could try to predict it. We could read scary stories in the press about it, but I wouldn't get too worked up or worried about it, because if it's happening, and we don't know if it is happening, but if it's happening, it takes about 10,000 years to happen. I like to say that predicting the next reversal is like predicting the next bull run on the stock market, all right? You don't really know that it's happening until it's half over, okay? And it might go down again. So there we go. That's my answer about reversals.
The way it was talked about is like one day we'd wake up and everything would be changed, and
yeah, that's not going to happen.
Yeah, not going to be that way. Okay, good.
I think at this point, yeah, I think we should let people go that need to go. I will leave this call open if people want to continue chit-chatting. Dr. Love, you're more than welcome to stay on if you want to and answer more questions, but I thought I'd bid everybody good night and thank you all for coming.
Thank you.
Yeah. I'm happy to stick around for a couple more minutes. I don't want to force you to ask me